Hi everybody, and welcome back to the third episode in our series where we go in-depth into difficult and seemingly mind-boggling concepts that you will encounter as you embark on your mathematical journey. For this video, we aim to go through trigonometry and break down its absolutely staggering amount of formulae and definitions. In a way that is kind of ironic to this video series, we will not truly go in-depth into this subject, due to its titanic scale and high levels of intricacy required in higher level questions, especially involving identities. However, we strongly encourage you guys to do your own research if you find any of the foundation concepts we discuss interesting. If you already have prior knowledge regarding these concepts, this video can also serve as a refresher course. Okay, with that out of the way, let's start to peel this trigonometric onion open. Firstly, let's go through some common misconceptions many students, including I, believed when racking our brains against the wall, staring at a question that requires us to derive a sub-formula from a formula that was originally derived from another formula that was derived from a unit circle definition. Looking at you, half-angle formula. But I digress. It does get easier once we get these misconceptions out of the way and realize that hey, trig isn't really that tough. When we first are introduced to trig formulae, we may not understand that theta, beta, or alpha are used to substitute actual angles, and that each one is not different from the other. For example, let's take a look at the Pythagorean Identity, which we will discuss in detail later. Sine squared theta plus cosine squared theta equals to 1. We can just think of the two variables theta as a glorified unknown x. Therefore, when we get to more complex formulae that utilize more than two unknown variables, alpha and beta, we can just think of them as x and y. Another important thing to keep in mind is that all trigonometric functions are essentially ratios. In a perpendicular triangle, sine refers to the ratio of the side opposite of the angle over the hypotenuse. Cosine, the adjacent side and the hypotenuse, while tangent is the ratio between opposite and adjacent. Usually, to help beginners memorize, the phrase SOHCAHTOA is coined, or basically sine equals opposite over hypotenuse, cosine adjacent hypotenuse, and tangent opposite adjacent. Moreover, it is given that cosecant, secant, and cotangent are simply the reciprocals of sine, cosine, and tangent respectively. We also know that since tangent theta is the opposite over the adjacent, we can look at SOHCAHTOA and come to the conclusion that tangent theta is no more than sine theta over cosine theta. By looking at the complementary angles in a right-angled triangle, the angles that add up to 90 degrees, we know that sine theta is cosine 90 degrees minus theta, or cosine pi over 2 minus theta, if you want to express it in radians, or the cosine of theta's complementary angle. The co in cosecant, cosine, and cotangent also means that when they are applied to the complementary angles of its corresponding function, they will give the same values. So for example, cosecant 30 degrees is the same as secant 60 degrees. If you were wondering what I was talking about when I described 90 degrees as pi over 2 radians just now, well, let me explain. 1 radian is the angle subtended at the center of a circle by an arc equal in length to that circle's radius. Notice that to cover the circumference of the circle, we need exactly 2 pi radians. Based on the previous video, the circumference of a circle with radius 1, or diameter 2 units, is simply 2 pi. Hence, we can equate 360 degrees or 2 pi radians, which means pi radians is 180 degrees. Radians are more useful than the more arbitrary degree or gradient system. Radians are the natural measure for a circle. It is based on an actual part of a circle and applies for all circles, instead of the more arbitrary degree system. You will find that radians are much more popular in higher level maths like calculus, so it's good that we grasp its concept early. The trigonometric ratios of special angles is a pretty extensive table that we have to memorize to solve trigonometric equations without calculators, and can be one of the first intimidating aspects of trigonometry to beginners. However, there is a really simple trick we can use to completely trivialize the extensive brain power it takes to memorize the values by heart. Firstly, we have to express the angles as fractions increasing by 1/4 for each angle. Think of it as something similar to the 4 quadrants in the unit circle. To get the sine values, we have to square root each corresponding quadrant. To get cosine, we just have to reverse the values in the sine row. Since we know that tangent is sine over cosine from the SOHCAHTOA definition, we can simply divide the sine values over the corresponding cosine value. Now we get into arguably the most useful set of trig identities, the Pythagorean identities, derived using Pythagoras' theorem, which is basically the square of the hypotenuse equals to the square of the opposite plus the square of the adjacent. From the unit circle as shown, we can express the hypotenuse as x squared plus y squared equals to h squared. Now, if we divide both sides of the original equation by h squared, we can derive cosine squared plus sine squared equals to 1, which will be our first identity. We can further derive two more identities from this current one. If we were to divide both sides of the second equation by cosine squared theta, it will give us 1 plus tangent squared theta equals to secant squared theta. Or, if we were to divide both sides of the second equation by sine squared theta, giving us cotangent squared theta plus 1 equals to cosecant squared theta. A quick side note, we manipulate trigonometric expressions similar to algebraic expressions, as they share similar properties when performing simplification or using identities. Graphing trigonometric functions is a good way to visualize how they work. The general formula for any trigonometric function is a multiplied by f bx plus c, where the function f can be substituted for any trig function. A stands for the amplitude of the graph, or the vertical distance between the axis of the curve, which is the line that splits the curve into two congruent sides, which is not the same as the x-axis, and its turning point. B determines the period of the graph, or the coordinate on the plane where the graph repeats itself. C determines the axis of the curve. For example, let's use the graph of 2 sine 3x plus 4 to illustrate how these variables can affect a trigonometric function. First off, the axis of the curve is 4. The period of this graph is 3, so the graph repeats itself every 2 pi over 3 radians, or every 120 degrees. Since we know a regular sine function reaches 1 at pi over 2 radians or 90 degrees and negative 1 at 3 pi over 2 radians or 270 degrees, we know the turning points will be at 30 degrees and 90 degrees. Also, since the amplitude is 2, we can find the turning points as 4 minus 2 and 4 plus 2. All trig graphs are also recurring, so the exact same graph will repeat for 120 degrees to 240 degrees, and so on. It is very important that we should relate the graphs for sine, cosine, and tangent to the cast system, which gives us an arbitrary understanding of what quadrants have negative or positive values for certain trig functions. As I'm sure all of you are aware, trigonometry involves the study of angles and side lengths in triangles. It emerged way back in the 3rd BC, following Alexander the Great's death. Since then, it has seen wide use by early Hellenistic humans trying to understand how nature works without immediately crediting it to the Olympian gods. It has proven helpful in calculating the height of tides in oceans, as well as the heights of mountains. Sine and cosine can also appear in nature as well, in the form of sound waves, ocean waves, and light waves. Even though trig may seem like the most abstract topic you have come across so far in mathematics, it is actually one of the most practical and grounded in reality subjects out there. One of the most widely used practices of trigonometry is bearings. Sailors regularly use trigonometry in the form of compasses and maps to set directions and pinpoint their position in a large featureless ocean in relation to certain landmarks. Triangulation is also used extensively to pinpoint specific locations using angles from 2 points through a fixed baseline. Mount Everest's height was measured this way, back in 1953. It is also the main method astronomers use to calculate the distance of astral bodies to Earth. In conclusion, trigonometry is a fundamental aspect of mathematics that has helped elevate our civilization to the postmodern era we live in now. Without trigonometry, we would not live in a world that is globally interconnected, thanks to outer space satellites, or had the privilege to behold beautiful buildings that are testaments to human architectural prowess, or be able to play games more technically advanced than Paul. If you like our content, make sure to hit like and subscribe, and we'll see you next time.